Welcome to this TAS Academy HVAC training video. Today's topic, reading wiring diagrams, sequence of operations, and using sequence of operations to troubleshoot. Part 1, wiring diagrams. With your host, Randall S. Ripley, Technical Support Manager and Trainer at Total Air Supply in Derry, Manchester, and Nashua, New Hampshire. And as I said, part one that we will be discussing today is wiring diagrams explained. We will start off with this. This is a three-part series going through wiring diagrams, covering types, various tips on reading them, etc., so that you will have a better understanding of the next two parts of this series. The ability to read the ability to read and interpret wiring diagrams is perhaps one of the greatest skills that service technicians can master. Due to today's equipment becoming more and more sophisticated in their control schemes, it is extremely important that technicians master this skill. Two important things in circuits we need to understand. A switch is a control or circuit protection device that is considered a voltage passing device. For example, limits, fuses, rollout switches, contactor contacts, relay contacts. A load is a current or energy using / consuming device. For example, motors, contactor or relay coils, light bulbs, electric heat strips. Again, switches are a power passing device. Depending on the equipment, you may encounter many different types of switches. And let's see if I can get this. There we go. Depending on equipment, you may encounter many different types of switches. You should familiarize yourself with the different types. And as we see here, we've got overloads that are thermal, contacts, normally closed, normally open, push buttons, just other types of switches. Here we see with timed, normally closed, normally open, timing open, but you don't see these so much in just general diagrams. Switches, you have flow, normally closed, normally open. Normally, these are just a generic set, normally closed, normally open. Limits, temperature, you'll see this symbol frequently, normally closed, normally open. And pressure, liquid, these are little floats. A fuse, a generic coil, circuit breaker, a motor, indicator light, excuse me, and a transformer. Loads are power-consuming devices like light bulbs, motors, heaters, and other devices that consume or use power. It's important for everyone to remember that before any circuit can function, there must be a complete path from the power source through the conductor and switch power passing devices to the load power consuming device and back to the source. So if we look here, we have the power coming out and going down. The switch is closed because it's on. The light bulb lights, and the power goes back on the neutral to the power source. We look on the other side, and this is a line voltage circuits, and the power's out, but it's going to stop right here at the switch because the switch is off. So we don't have a complete circuit. The power can't light the bulb. And low voltage circuits work the same. The common is the neutral of the low voltage circuit. And as we see here, we've got power coming out on the 24 volts, comes down, crosses the switch, light bulb's on, and back to the source. And the same here. But the power stops again because the switch is off. So there's not a complete circuit there. Nothing's going to happen. Here we go. Diagrams are read in the de-energized position, which means that, this, like pressure switches, obviously they're going to be open because the inducer or the power venter isn't on. So you see all your pressure switches are open. All your limits here are closed because they should be. If you have an open limit, that means that your unit's not going to operate anyway, or at most, if one of your limits are open, the blower is going to be running all the time. The transformer is the dividing line between the 120 volt line voltage and the 24 volts AC circuits. Let's look at some symbols in this low voltage section of the ladder diagram. There's your fuse, as we see it up here. There's our fuse. Here's our low voltage connections. That would actually be the low voltage connections on the board in this portion of the ladder diagram. Here's contacts that close to power things and stuff. As we see here, we're powering. We have our power come through our manual rollouts, and when this closes, that's your gas valve being energized. And this is a two-stage gas valve, so the second stage would be here. I'm struggling here, folks, with my laser pointer. And then contacts. So, and to the micro switches, they tell the indoor air circulator blower what mode and speed it's going to run on. A diode is a device that only allows voltage to flow through it in one direction. Basically, it's the electronic version of a check valve. The arrow indicates the positive side of the diode, while the vertical bar indicates the negative side. You can think of it as the positive side flowing into the negative side, with the arrow indicating the direction of flow. In the furnace control board, diodes also convert the AC voltage to DC voltage to trigger electronic switches to activate functions of the furnace. And they also can be rectifiers, signal limiters, voltage regulators, switches, signal modulators, and LED lights, light emitting diodes on furnace control board. And reverse polarity is crossing the line voltage and the line neutral connections. In this case, reverse polarity or reverse phase could and does cause problems when you're trying to feed power the wrong way through a one-way switch. In this example, we are on the line voltage side of the circuit. And we have the door switch here, and there's our line voltage there. We're on that side of it. We have several contacts that when they close send power to the item they are in line with. And on the other end, we have the neutrals that provide the pathway back to the electrical panel. Pictorial versus schematic diagrams. While the pictorial shows you the components and their wiring to the board in a picture form, the schematic or ladder diagrams show you the direct electrical relationship. Many manufacturers include both. There are advantages to both types. Some technicians find one type easier to use than another. The power venter relay coil is on the low voltage side. The power venter relay contact on the line voltage side. And we will see this in several examples here. The IDBR1 indoor blower relay coil is in the low voltage section, and the IDBR1 contact is in the line voltage section. And the same for the IDBR2. The coil is in the low voltage, the contact is in the line voltage. The hot surface ignition relay coil is in the low voltage section, and its contact is in the line voltage section. So, you're seeing that all your relays, the controls, are 24 volts. The contact part, the coil part, and the contact carries line voltage across it. The pictorial diagram is very useful for locating the approximate position of the components and connection locations. Wire colors or numbers are often included on pictorial diagrams. The pictorial gives you the 9-pin connector plug and allows you to trace out the wires to each connection. Although useful for these reasons, the pictorial is usually too confusing to use for diagnostics. Since the schematic or ladder diagram follows a ladder logic, it is easier to follow the sequence of operation. The red wires in this diagram are line voltage and power the control, the module control, and the transformer. And blue wires represent neutral wires. Neutral wires are white, but you can't use white wires on a white background. The low voltage wire and line voltage also wires can color code. On the diagram, the pictorial always tells you the colors of the wires. We have component code here, and again you see these components here, and that one is the CCR, compressor contactor relay. Then we have the HVDR, high voltage defrost relay, and the LVDR, which is the low voltage defrost relay. Wiring code, you're going to see there's a factory wiring, here a solid line for high voltage, smaller solid line for low voltage, optional high voltage is got the dashes, and then field wiring over here. Be sure to always read the legend included with most diagrams. Many times notes are included that are important for the technician. For example, this note explains where unused motor speed leads should be placed. So let's do a little bit of side-by-side comparison of a pictorial diagram and a ladder diagram. So as we see here, we have a diagram that the pictorial section on the left here is looks like a furnace. shaped like a furnace, and you have your line dividing the burner compartment and the blower compartment. As you see here, the left side and very top right, the pictorial diagram. As we said, it kind of looks like the furnace. And it just shows you in general location of the components inside the cabinet. And then we have the right side, from the red line near the top to the bottom is the ladder diagram. And we see all of our low voltage components from here on the transformer down, and then our line voltage components up above that, because the transformer is the dividing point. And as we said, the cabinet's going to divide that. There's our transformer, the dividing point in the line voltage and the low voltage, the pictorial, excuse me, and the schematic portion of the diagram. These designations are on the low voltage section of the ladder diagram, tell us something very important. And what they're telling us is that these numbers is the point, the slot in the 9-pin or 12-pin or 15-pin connector where those wires go into that connector. And again, the 12-pin connector here, we see this one has a 12-pin, and all of these numbers are these numbers here. And furnace boards can be 9, 12, 15. But that is, by the time we're done with the third section of this, you'll see why that is so important. Because we're going to use part 2, video 2 is going to be the sequence of operations, and then part 3 is going to be using the sequence of operations to troubleshoot. We'll talk more about that at the end. So low and high fire pressure switches. We see our pressure switches up here, and here they are in the schematic. And you see this is a little bit more of a blown up version. And here's our pressure switch, front cover pressure switch here and down here. So the animation that just happened there, I'm showing you the pressure switch closing because this is a 2-stage gas valve. And they're breaking the common, because remember, we have to have that circuit all the way back from the power source back to the power source. And if we break this common, we don't need to break both legs of this power, because this is not going to work without that common being back to the power source. And that's why we break that. You don't have to break it twice on 1 and 2. You're just breaking it with the common. And you could apply voltage there all day and nothing's going to happen. Auto reset primary and auxiliary limit controls in the pictorial versus the ladder. And here we see the auto, here's our primary and here's our autos. Our primary is actually this one right here, and the autos are these two. And here's the a blown up version of that, so you see it a little better. And there's your primary, and here's your 2 autos. And the limits are automatic reset anyway. But don't forget about those 2 auxiliary limits, because If you're getting an error code that says open limit, those and that primary limit is not open, most likely one of those auxiliaries is open. Manual reset rollout. Here they are. Here. Just remember that it's manual reset rollouts are reset for a reason. That's a much more bigger issue if you've got rollout occurring, because you got flame rolling out of your burner area, out of your burners, and that can be putting carbon monoxide in the room also. And that's why it requires a qualified technician to check out the unit and figure out why rollout is happening. And the furnace, that's the furnace's way of letting you know that you need to get someone out there. Because remember, if it goes out on rollout, it doesn't come back on until somebody pushes the button of the rollout that's tripped. And if a rollout or a limit switch keeps tripping, the switch is most likely doing its job. My suggestion would be do the testing necessary to determine the cause before wasting time going to the supply house. And we will talk about those tests specifically in the third video. The new Comfort Bridge versions of the units can tell you which limit category is causing the fault, and it could be the auxiliary limits, the rollouts, the primary limits. It can be any of those three. Now, the primary limit and the auxiliaries are all in series there, as you see right here. So it's not going to tell you which one of those it is. And your two rollouts, they are in series as well, because remember, control circuits are series circuits, and your loads circuits are parallel circuits. And we'll discuss that in a second. And here's how it works. A pink wire from the 10 pin in the plug goes to the auxiliary limits. At the exit to the auxiliary limits, the voltage splits. The red wire goes back to the plug to let the unit know if either of the auxiliary limits are open. Obviously, it doesn't go back if one of those auxiliaries are open. So by the power making it back to the plug, that means that those limits are closed. The black wire jumps up to the primary limit. The purple wire off the other side of the primary limit goes back to let the board know it's closed. The blue wire jumps up to the rollout switches, goes across them, and comes back on the orange wire, meaning that those switches are closed. Now we have the flame sensor, and we see the flame sensor here, and we see the flame sensor in the schematic here. And we have now moved over to the line voltage side of the transformer. The flame sensor has a voltage on it that is used in the flame rectification process. See the service manual for flame sensor voltage. And then the igniter. And here's your igniter up here in your pictorial. There it is in your schematic. And obviously we've got this bigger version so you can see it a little better in the schematic portion. The power venter. Just remember that officially, or actually, whatever way you want to term it, it's a power venter in a 90 plus unit, because the PVC vent is sealed, and the venter motor is actually pushing the flue gases out. Uh, a draft inducer is on an 80 plus unit, and that acts as a regulator of air through the heat exchanger. But it also, if you ever look at the tables, is a fan assist unit, because the fan does assist the flue gases a little bit, but the natural draft of the flue is what really vents the flue gases. But on a 90 plus, and even the manufacturer's reps will call it a draft inducer, but it actually is a power venter because it's a sealed system. And remember, we're condensing, lowering that flue temperature all the way out to the termination point. Mm-hmm. And it's a two-stage power venter, and you can tell that because here's our main power contact, and then we have a normally closed and a normally open. So here's our normal first, here's our high and here's our low speeds. And the transformer, basically the big thing about the transformer is that it's 120 volts AC line and 24 volts low voltage. And it does that through induction. And it's actually a buck transformer, but it's better known as a step-down transformer. In this case, it reduces the primary voltage of 120 VAC to 24 volts VAC control voltage. And if we was to look at the board here in the pictorial, here's the board in the ladder, these 3 points. So we look at that, and again, all of these are in series circuits, and these are series parallel circuits. They're wired in parallel for the power, so that each one gets equal voltage, but maybe the amp draws are different, so you'd have different amperage readings. But they get all the same voltage here. That's why it's called parallel. And the series part of it is because you've got switches to control them. Because something's got to be in line with that power so that when you don't want the thing to operate, or the control itself doesn't want it to operate, it can turn it off or turn it on. And the blower motor, it's electronically controlled. It is an ECM constant torque motor, meaning that it is different than a variable speed constant volume. Because this motor, if it has the right torque to it, even if it's not supplying enough air, it won't ramp up to hit that airflow mark, because it sees the torque that it wants to see. Now, ECM constant volume will ramp up to achieve the CFM that you've set it for. It doesn't modulate up and down, but it does try, ramp up to get to that speed. And then you have modulating now, from like modulating equipment. If you've got a gas furnace that modulates from anywhere between 50 and 100%, then that motor's got to go up and down according to the percentage of the gas that's being used. It's we're only operating at 55%. Well, the blower speed's got to slow down to keep a constant temperature rise for that 55%, or to wherever it modulates to. And you notice that it's on the schematic, it's in the line voltage side and the low voltage side, the indoor blower motor. And the reason for that is that this side represents the low voltage control wires, and this side represents the power. And again, this is a diode. And we just talked about that. Now the blower door switch. This door switch, if it's not closed, the panel pressed against it, or you got a screwdriver in it, I prefer my little magnet, then the power's off. But sometimes you need that blower door off and make sure that it's powered, to keep it powered so that you can test something or whatever. This is what I like, my little stud finder magnet. They're very strong. They hold that thing together. I actually like it so much I have a video on our website for it, about it. But I like that. Again, other people might like tape, screwdriver, whatever. I mean, whatever works for you, works for me. So the blower door switch in the pictorial, the blower door switch in the schematic. Now, on this, the reason I put this here, I just want to show you that here's our door switch. The power comes down from there, and it goes all the way to the transformer. And you have all these legs of it that come off it, and that's why it's called a parallel circuit, because all of these are in parallel. And they're series parallel circuits, as I told you, because, if series parallel circuit has the parallel power, but it has to have a switch in series with that each thing, because something's got to control when that's coming on and when that's not coming on. Because there's all our loads and they're all in parallel, but you notice there's switches to control them also. In part 2 of this series, we're going to take an animated walk through the sequence of operations for the Amana R32 AR9T96 two-stage furnace. And why I say a little animated walk is that we're not going to have pictures of furnaces, lighting, and all of that. Everything that we do in this is going to be on the diagram so that you see exactly what is going on, but on that diagram. And as you can see here, we've got the igniter lighting and the flame has lit. The igniter will be going out shortly. There's our little inducer. We have blower fan motors and stuff we'll be bringing on. But that's why I've designed it this way, is so that you will see everything that's happening on the diagram instead of seeing it on a furnace. This helps you really understand these circuits, because we've got the plug and play and all. So hopefully you'll be coming back for the second edition, the second video. And then on the third video, we'll use these same diagrams, but we're going to troubleshoot every step of the way through that. And again, will be all on here. Your test, all of that will be done right on the diagram. There'll be no, as I said, pictures of furnaces or anything like that. It's going to be that diagram with components and all that, and that's how we'll troubleshoot it. In part 3, as I said, we'll go through the troubleshooting. So if you like this video, please hit the like button. Subscribe to our YouTube channel to get all of the new videos as they drop. You can go to our video site at this address here. And I want to say thank you for watching. I hope you come back and complete the series, because if you do all three of these, I think you'll be pretty good with diagrams and troubleshooting with sequence of operations. So once again, hopefully you'll be back for the next video, and thank you for watching this one.